So we will start today our second term seminars. And today we have Aviv Solodoch from Hill. Aviv is a physical oceanographer, and he studied a subject from multiple scales, as he will probably say better than me. And before that, he was a researcher at Tel Aviv University, and he did his postdoc and PhD at UCLA. So please, stage is yours.
Thank you, Neta. Thanks all for being here. So, I should turn this on. Okay. Show me. Okay, so I'm going to tell you today a couple of stories about cross-shelf transport via sub-mesoscale vortices, and I'll explain the terminology. This is joint work with all of the people listed here, especially with Chezi. It's not here today, I think. Okay. So, why do we care about cross-shelf transport? I'll touch on this lightly because I think it's pretty clear. We have materials which are either desirable or not, and become also when they cross the shelf. So we're talking about marine oil spills, terrible things that can happen and do happen from time to time. And our region of the sea is being developed and used in that regard in terms of gas. So if that happens, if there's a oil spill, gas spill, will it make landfall or not? So what determines that? That's one of the things that are determined by cross-shelf transport. And there were important examples of this in recent history, such as Deepwater. Anyway, I forgot the name for a second, even though I was part of that campaign to measure it. So anyway, another thing is supply of nutrients. So the shelf is much more rich in nutrients, shelf in the coastal area, in the deep sea, especially in our area. The Eastern Mediterranean is an ultra-oligotrophic sea. There's very little productivity in it, in the deep sea. So any material that crosses, water that crosses the shelf can typically bring with it more nutrients and enrich the offshore environment. So it's important from a biogeochemical perspective. And another viewpoint of pollution is that we also release it from shore via river outflows, for example, and other means. And whatever anthropogenic materials are released to the coastal environment will either stay there, which is also usually not desirable, or get somewhere else along the shelf, across the shelf, and it's a difficult problem to determine a priori. So the processes involved are partially understood, and there's a lot more to learn. I've put a few pictures here with the examples. So that's just one of the gas platforms we have in our area. Use the pointer in the waters. These poor sea turtles are from the disaster we had, when was that? Early in 2022, when there was the tar that basically covered all of our beach areas. So that had strong ecological implications. I think a couple of researchers here have also worked on it. This is an illustration of the high chlorophyll content, proxy of the productivity in the coastal area, and an example of it going offshore in a particular case. And what you see here is an example of basically it's a density current or a nephelate layer which originated from a river outflow, likely. This is around the Alexander River outflow. And you can see how it traveled. This is 25 kilometers offshore, and it keeps going, and it brings it whatever has originated from that estuary. In this case, what's shown here is turbidity, but it carries its materials with it. Okay. So part of the problem with these things is that there are many scales of flow in the ocean. So you're dealing with multiple things at the same time. There's little swirls and bigger ones, and they're all embedded inside each other. There's different types of flows, different time scales of change. It's the problem of turbulence, really. So these are, again, a couple of illustrations. This is from the Deepwater Horizon. That's a name I couldn't, for some reason, couldn't come to mind earlier. Deepwater Horizon oil spill, the worst oil spill in history. And it's some sort of aerial imagery. I think this is just a plain RGB image. And you can see the oil plume here. And you can see a lot of the meandering that the flow does. Basically, it serves as a tracer for you to show the flow path in this case. You can see different scales of meandering and vortices and so on. So this is, when you try to determine where it goes, all of these things will influence it in addition, this internal variability, in addition to external forcing. And this is a chlorophyll reconstruction from satellite based on multispectral imagery. And this is in the Pacific, I believe. But the point here is that if it's clear enough from where you're sitting, it really shows a lot of different scales. And it's a little convolved with the fact that there's different scales of productivity as well. It's different scales of the biological system too. But you can see how basically if you have a local maximum concentration, how it's filamented and stretched and kind of moved around locally. So it's a complicated problem in general to understand flow in the ocean, and we're talking about the coastal area or shelf area. And I'd like to go to these smaller scales that I've alluded to, and then I'll talk about bigger vortices too. And this is an example from a very large scale campaign with a lot of participants that took place in the Gulf of Mexico in the area of the Deepwater Horizon oil spill. It was funded by the oil spill guilt money, which was a lot. And I was actually on the airplane taking this image at the time. And what you see here, I'll run this video in a second, but this is thermal imagery, so infrared imagery. So what you see here is sea surface temperature. It varies over 1.5 degrees or so. And there's what's called a hammerhead or mushroom head here. And it's basically two counter-rotating vortices. There was some sort of jet, and it spinned vortice going this way and that way. Or I guess one is sort of more in the center. But that's usually the type of flow that you get around this. And I'll just run it. And I should mention what was done here is a very large number of drifters was released inside the flow. So there were multiple ships working on this at the same time, releasing these drifters. It's just a drifter is just a passive instrument, has no self-propulsion. You just put it and it floats in the water. And it has a GPS transceiver, so you can measure its motion and its velocity. So what you get is basically a map of the water velocity, because it moves with the water passively, of the water velocity in an entire area, sort of tightly mapped. So let's see what it does, and then we'll talk about it. Okay. So there's more and more of them because they were seeded sequentially, and now they're starting to do some interesting things. So they're converging. And if you notice the scale of the convergence, like from the scale they started to the scale they got, looks like a point. Yeah. It's really crazy. So I'll run it one more time, and basically now you'll see that there's two different colors of drifters, just colored here for the movie, and the purple ones are the ones that will converge to a point at the end. So you'll see that a lot of them are basically covering the same area, and they're white, and they won't reach the same place. So they were in the same area, but they left for some reason. and some stayed and converged. So this basically only makes sense if there's different scales, small scales which can sort of move some of them from the same large area to different areas before they can converge. And now I'll show the more qualitative analysis of this in the paper. I should say I'm not on this paper. I was on a plane, but I didn't write this paper. So, okay. So what you see here is basically just snapshots from the movie. And it's all the same scale, 10 kilometers in the first three, and then they blow it up. This one, 60 meters. So this point that they all converge to is just 60 meters. It's orders of magnitude of convergence. And now they took all the drifters and they write the pair separation in the y-axis here. The x-axis is time. And you see that there's sort of two things going on. Some of them are very far from each other, up to 100 kilometers or so. And some of them remain very close to each other, or even get closer with time. They start at 10 kilometers and they get 1 kilometer or less. And there's two things going on at once. And then this is how it was resolved. They sort of applied some sort of clustering method to the groups of drifters, and they saw that basically the drifters within clusters converge. Some of them do a lot. That's just the within cluster separations. So that decreases over time. But the distance between clusters, which are sort of the bigger scales here, they increase. So you have those larger clusters or larger eddies that on average just sort of diffuse away from each other. But within each thing, you can have multiple smaller cogs or machinery processes which tends to converge material. So obviously, if you want to understand material transport, you got to understand the smaller scales as well. And the reason this is, I'm going this way about it, I kind of say what you have to, I'm emphasizing that large scales are enough, is that classically the larger scales, larger than, say, 10 or even tens of kilometers is what was studied in physical oceanography, partially because that's what the technology allowed. It's very difficult to measure those smaller, faster moving things. It's very hard to sample them. And so let's get back to our region, because this is where the results I'll show you are based, even though the problem is universal. So these are some classical maps of different theories of or conceptions of the flow in the Eastern Mediterranean, and different researchers or consortia have arrived at the conclusion that there's either this boundary current in the shelf and slope area going around our Eastern Mediterranean, and that's a dominant flow, or that there's more interior pathways and recurring, this is the more modern view that came, and these recurring mesoscale vortices, which really recur in the same areas to a large degree. So you have these vortices, which are basically revolving paths of flow, and they tend to, for some reason, I won't get into that, they tend to recur in the same areas in our region. There's also transient ones, but in any case, the mesoscale vortices are tens of kilometers or over 100 kilometers even in some cases, size. And what is important to say about them is that they are in geostrophic equilibrium. What that means is basically that the pressure gradient inside them is balanced by the Coriolis force. So the Earth's rotation is a vital part in sort of maintaining them, Coriolis force, through the Coriolis force. And that's a major constraint on what they can or cannot do. So it's kind of, you can say it's difficult for them to cross, to go down bathymetric slopes, for example. That tends to cause changes in the circulation, which is a lot. And it's basically that, the ballerina effect. So if you turn and you stretch your arms, you turn slower by conservation of angular momentum. And same thing happens to eddies or vortices, and these vortices are sort of slow relative to the Earth's rotation. So this effect basically is a too strong effect for them to kind of maintain their general properties, speaking roughly here. And that's the important thing to remember is that I'll get to this parameter later, which characterizes their let's say, their strength relative to the Earth's rotation, and that's the Rossby number or the vorticity. We'll get to that later. But that's about mesoscale vortices. And in more modern view, we have satellites which go over and capture the sea surface elevation, which is a proxy of the circulation because of geostrophy. So lines of constant height are also lines of constant of flow or stream function. And we see all of these things. We see the boundary current, and we see the recurrent eddies, some internal punctures. All of these things are true at the same time. But a major thing that was noticed in 2000 or even slightly before, but haven't been really followed up on since, is that there are these much smaller things called sub-mesoscale. So sub-mesoscale for smaller than mesoscale, obviously. Sub-mesoscale vortices, and they can be, look at the scale here, this is 8 kilometers. You see the swirls here, so each one of them is let's say 6 kilometers or so, each one of these vortices, or spirals as they were called at the time. So these were seen from the space shuttle. The NASA put a oceanographer on the space shuttle because they noticed these things, and they put him there and they asked him to document it and observe, and he took a lot of pictures with basically a handheld camera, and it actually was what the material used in this classical paper by a different big shot oceanographer, Watermark. And this is a couple more pictures from this paper. You can see this, the scale always. These are always very small things, and they're always close to shore. I'm showing where they are. I mean, in all of these observations, at least, they're pretty close to shore. This one is even much sharper. It's just these fronts, these lines are basically just a couple of kilometers, or sorry, 100 meters maybe wide or so. Very narrow. And I guess I'll skip the last one here. Okay, so this was realized already in the year 2000 or before, and this was the first observation, or one of the very first observations of the sub-mesoscale circulation globally, anywhere, but it hasn't been followed up, whereas in our region, whereas generally this is one of the forefronts of oceanography, sub-mesoscale circulation. This is one of the things that people have been working on very strongly in the last decades, trying to understand. And the reasons are what I've said before, that they have important properties in terms of material dispersion. They converge material very well, but also they have other interesting properties, which are also related to that. So one, the vertical velocities inside them can be orders of magnitude higher than the mesoscale vortices. So again, if you care about bringing stuff up or down in the ocean, if it's for ventilation, if it's for nutrients uprising or anything like that, it's important. And lastly, they're important for just plain physical oceanography reasons, namely they tend to merge and force and basically transfer energy to the larger scales as well, but I won't get into that. So I want to show first, last year we published a paper about this topic, sub-mesoscale circulation in the East Mediterranean, and this was based on, we did some modeling work, we did high resolution numerical simulations. So I'll just show some results from that as a motivation for the main part of the results, which are recent observations that we did, where we have managed to track a sub-mesoscale eddy, a coherent sub-mesoscale eddy, which has lived, lived for like 2.5 weeks, and we tracked it throughout the entire time, and there's almost no examples of such observations globally. Full complete life cycle and so on of a coherent sub-mesoscale eddy. So I think it's quite useful, and I'll start with this model. So what we did here, we ran a numerical simulation. So basically, we solved the equations of flow and heat transfer and so on in the sea, forced by the atmospheric state from a realistic, basically from a numerical weather prediction model. And that's all I'll say about it. And it's basically this has to run on a super computer cluster. So to be conservative, we ran it in a nested fashion. So the outer area that we care least about for our purposes it was in a rougher resolution, 3 kilometer resolution, which is still relatively high. This was in 1 kilometer, this was in 300 meters. So you kind of, I mean, you solve them sequentially and use them to force the next one. And that's one way to be able to do these things. And what I'm showing here, and this is for some reason, is there a way to, I think it's out of focus. Is there, anybody knows how to focus? Huh? No? Too bad. It's really, you can't see the detail. Okay, well, you're going to miss a lot of eye candy. So, in any case, so what you see here is the vorticity. That's the variable plotted, vorticity of the sea surface. So just, I'll show you some more plots of vorticity. So it's just important to remind people what it is. Vorticity is basically a measure, or you can think about it as an analog of angular rotation rate, but it's a more useful quantity for fluids. And it's useful to remember that if it's sort of a round feature, such as a vortex here, then the vorticity in it is a measure of its rotation rate, or twice its rotation rate, really, exactly, for a very small one. And if it's an elongated feature, like a filament here of stretched material, then the vorticity is more likely, and this can be quantified exactly, but generally it's more likely related to the shear, the change. There's a different flow here than here, different strength of flow along it, then that would be, the vorticity would be due to that. So that's vorticity. It's a measure of either shear or rotation locally. And the units we will use will be such that it will be scaled by F, which is twice the Earth's rotation rate. And with that normalization, geostrophic flows, so large eddies, mesoscale eddies, have very small vorticity, 0.1 or less. Whereas sub-mesoscale, they have order 1 or higher vorticity in this scaling. And what it means is that basically their inertia or capability to transport their own momentum is stronger than the Coriolis force. So they are less constrained by rotation. That's part of the reason they can do sort of more interesting things with material transport. Okay, so that's the model, general mean stream function versus observations from satellite, just to show you it does a sensible job. I won't show you any more validation, but I want to show something about the boundary current. So here these lines are stream lines, so meaning the mean flow is along these lines, okay? So you see that they're bunched more close to the boundary, and the bunching closer together means faster velocity, basically, higher velocity. So there's this jet of boundary current flowing along the continental shelf and slope, and that's a typical thing, and it goes anti-clockwise. And this is the mean current. If you take a section here, I put this black line here, if you measure the velocity in a vertical plane, this is what it looks like on average. So it's about 20 centimeters per second, and it goes up to about 100 kilometers from the coastline. That's the basic facts of life outside our coast. If you go out on average, that's what you'll see. But in practice, it can be anything on a given day. Okay, and it carries about 2 million cubed meters per second. That's about twice of all world rivers together. It's not a small amount. So it has quite a high transport. Okay, so I'll show you a movie of vorticity from the simulation. And again, the resolution is not great, but in the projector. But what you see here is that now this is the year day, so we transition to summer, and you see bigger vortices in summer than we did in winter. It started in winter. Now we transition into winter again, or fall, and it's going to start making, the sea is making smaller vortices, sub-mesoscale vortices, and it becomes eventually this soup of tightly packed sub-mesoscale vortices. Run it one more time. Okay. So, and another thing to notice is that the boundary current is a major player in this. So a lot of the variability seems to originate just visually here in the boundary current. You can see it basically transporting a lot of eddies. Sometimes they grow, sometimes they detach from the coastline, from the boundary and go to the interior. Like here, there's an actual full train of eddies, which eddies and vortices, it's the same thing for our purposes, that are leaving the boundary and getting into the interior. Okay. So it's this, what I said, that the boundary is important for, it's a hub of variability and so on, can be quantified, so we can just plot the variability of the velocity, which is the eddy kinetic energy, the kinetic energy of the disturbances from the mean, and that's what you see here in the model. So you see that it attains some of its highest values at the boundary. So it fits what we see visually from the movie. And by the way, if you just use the satellite data to kind of do the same thing, it doesn't look quite the same, and that's to be expected. It's not a model error, at least not fully. Hard to know exactly. But we expect the satellite data to be biased low in this regard because its effective resolution is much lower. It has effective resolution of tens of kilometers. So it misses all of these sub-mesoscales. So you really need a numerical model for that. And we can go further and do the histograms of the vorticity in summer and in winter. That's in blue and in red. And in blue, the solid lines, you see that the positive vorticity becomes much higher, and that's what goes on in the interior. So you get much more cyclones, that's positive vorticity. But at the boundary, it's plotted in the dashed lines near the boundary, defined in some way, never mind exactly what distance from the boundary and so on. You see that year-round, summer and winter, blue and red, you have these higher elevated vorticity values. So again,
it's not symmetric.
True. Yes, that's a big puzzle. There are some theories of why positive vorticity or cyclonic vortices are preferred, and they're good theories, but there's a few different ones, and it's not clear if any of them is the right answer or not. There's a couple of ones that are, that at least they're sensible, but maybe I won't get into that now. All right. So what is? So I think you might be curious as to why it happens in winter. So the basic that's more or less well understood. It's basically because the mix layer in the sea is deeper in winter. It's thicker. So that's the mean density profiles in different seasons. In winter, that's in blue here. You see it's sort of more well mixed. It's more even. Whereas in summer, because of heating and so on, you have much warmer and lighter, less dense water near the top. So you have more stratification. Basically, so once it's mixed, the mix layer is deeper. Then, if you have now a difference horizontally between different places, you have two water masses coming. This is an average across the basin, but really the profiles will differ between different parts of the basin. They will still be well mixed vertically, but the density, say, near the boundary and in the interior will be different, okay? Because the boundary current brings water from far away, from the Atlantic, in fact. So now you have two layers of fluid at the same level, but one is much denser than the other. It's an unstable state. The stable state would be this way, that the denser layer is beneath the lighter layer. So it's basically energetically unfavorable, and you can release that energy in various ways, and basically from that you form the sub-mesoscale vortices. That's the basic. It can manifest in different ways, but that's just to address that, the elephant in the room. And it seems like there's nothing going on in summer. So what you see on the left is vorticity, basically the 95% of vorticity in black, and in red is the mixed layer depth. It goes in winter to about 100 meters. In summer, it's just maybe 10 meters. And there's very little going on. Vorticity is very low in the summertime. So are there no sub-mesoscales in the summertime at all? So we actually observed one, and we'll talk about this. Okay, and we've looked at the movie before, the animation, and we saw that there's a lot of events where vortices are formed at the coastline, and then, like here, they are detached or separated and go to the interior, see the interior with vortices. You can see a lot of these, different patterns, very pretty to the eye. Okay. But does it actually happen? So here's an example, one way it happens in the model. This is just after the bathymetric disturbance near offshore of Haifa Bay. And this is a blow-up. And this is the actual satellite imagery of fluorophil. You can see it looks very similar. So these things do happen. And they happen a lot. Actually, this is another chlorophyll patch that has went offshore, and there's more examples. This is another example of, this is a major separation point we find, and there's some observations which support that, but I'll skip it. And okay, this part is interesting. So I've talked about how sub-mesoscales are more capable of crossing the continental shelf and slope. They are less constrained. And let's actually examine this in a qualitative manner in the numerical model. So we're seeding passive particles. It's this square here. It's a bunch of particles, which are virtual particles, which are advected or moved around by the velocity of the model. And this is in summer, that's in winter. Let's see what happens. So it's advected along coast, but there's much more offshore transport. And if you can see it from where you're sitting, it mostly happens, that's in winter, it mostly happens by those sub-mesoscale vortices. They can be captured they can be kidnapped by an offshore eddy, which sort of pulls them, or they can move offshore in different ways. Whereas the bigger mesoscale ones in summer are less susceptible to that. Now, we talked about this. Okay. But notice, you can see some sub-mesoscale vortices, cyclones here, even in summer sometimes. You do get them in the model. Okay, so we have received funding for doing observations of sub-mesoscale circulation in our area, following the numerical work which we have done. And we wanted to start with the summer, just because of the timing we had. We wanted to start with the summer campaign to kind of test our new instruments and our plan and so on. And we didn't necessarily expect to find a sub-mesoscale vortex because it's summertime. But we did. And it's slightly different than the winter ones, we think. But it has some common properties. And so I want to show you results from that. And we took the Mediterranean Explorer, a ship operated by Eco Ocean, non-profit, and we used a bunch of different platforms. I won't describe everything today. I'll only focus on a couple of things. I'll mention also the glider from IOLR, which we have used. And I'll just introduce, okay, this was 2 days, and we went offshore from Herzliya up to 40 kilometers. And I'll mostly show results from these drifters, again, the same ones that we use in the Gulf of Mexico and that work I've shown you earlier. And we had these 2 big crates on the ship, and we just threw them to the water at select points, and we followed them via satellite communication. Of course, we didn't just throw them anywhere. We have identified an eddy, and some people were very pessimistic about the chances to identify a small eddy ahead of time, and with the state of the sea changes, you can't go whenever you want, and it's tricky. But I don't know if it's more luck than brains, but we succeeded. We did have luck. But we use different things. We use the glider, we put it in the water ahead of time, a week and a half before the ship, and we use satellite imagery, and we cross-reference, and we were able to find a target, and we were able to arrive in it and identify it with various instruments. I won't describe it. You can ask me that if you want. And then that's where we have put the drifters. Okay, so what did we see ahead of time? The data are here on top. This is chlorophyll imagery from satellite. And you see the elevated values, and then you see this meander of the coastal current. So suddenly this elevated patch has sort of left the coastal current, and it sort of did this turn. You can see it in sea surface temperature as well here. Maybe the contrast is a bit tough on the screen. But it's clear that it came from somewhere else. And 3 days later, it has rolled up, the meander has rolled up into what looks like a coherent closed vortex or closed patch. So we assumed that it is a vortex, a circulating flow. And the glider sections we took of it were consistent with that. So summarize just this. It's, I think it is important. We found that the filament ejected from the boundary current rolled up into a vortex, and it carried material with it, chlorophyll, up to 50 kilometers, not yet at this stage, but eventually up to 50 kilometers from the shoreline. And I'm just saying, I'll say it right now before you'll see it. Eventually, this material, much of it at least, stays offshore. So it dies. You'll see that the eddy will die, will stop existing and dissipate, and everything will remain offshore. So this is can be an effective transport mechanism. Okay, so 2 more days forward. Sorry, the eddy is still there. And 3 more days. This is already 8 days after the first image. And you can see it in sea surface temperature as well. So it really looks like a coherent eddy. Okay, I'll show you now a sequence of satellite imagery here. And this is chlorophyll in log scale. And if you're quick, you'll see that there's couple more eddies here. A couple more small sub-mesoscale eddies which were formed in the Lebanon area, except for the one which was formed here. And it will restart it so you can see. So around 16, you'll start seeing it. 15, 16. Now you see this, and it rolls up and so on. And in contours, it's sea surface height, which again is a proxy for the flow. That's flow lines. So basically, from this, it seems like the initial offshore flow was at least partially induced by an anticyclone, which has a mesoscale anticyclone, which has approached the shore. And it will come here. Now, this it encroaches on the shoreline, and then it has this sort of clockwise motion, and that's perhaps what has captured the filament after it was formed. So it might not have escaped on its own, but it wouldn't have been able to capture a mesoscale eddy. So once a sub-mesoscale eddy is formed, it can interact with things on the offshore and use it to kind of move off. Okay. And eventually, we can also see how it died, potentially. So this here is, I'll run it one more time. Eventually, there's a cyclone, and you won't be able to tell if it's a cyclone or anticyclone based on the contours, because I didn't mention their sign here. But there's around July, just July is around when it dies, when it turns to July. There's a cyclone which comes from the south, and it sort of merges with it. And okay, I find it hard to time it right now, but it's so I'll keep going. All right. So now I'll show you drifter motions. That's what you see here. These things swirling around, and the colored line that you saw was the glider path. So they started swirling around in a anti-clockwise manner, so that's consistent, that's a cyclonic eddy. And eventually they kind of got out of the eddy and moved north to different places. This is the complete trajectory over 3 weeks of the drifters. So they started in small recirculations, and after a couple of weeks, they kind of the turns grew, they became maybe unstable, and then they left it. Some of them, a couple of them left earlier. And then they either moved along the coastal current and beached either in Israel or in Lebanon, or some of them moved offshore. All right. Let's see what the time is. Okay. So we'll zoom in, it will be more useful. And I'm showing now, that's the glider, but the contours are now the chlorophyll imagery from the satellite. So you can see, and it's just one daily average, so it won't be exactly, but you can see that the drifters are revolving around the actual chlorophyll patch center. So it's all consistent, all right? And the glider, the color of the glider that I'm showing is the depth of the surface of a specific density layer. So it's an isopeak now. So inside a cyclone, what happens is that the density surfaces rise up to the surface, towards the surface. And that's what you see here. When, try it again. When the glider crosses into imagine that the drifters are sort of at the edge, some of them are at the edge of the cyclone. So now the glider came inside, and I'm going back in time, now forward. As it comes inside, it experiences a deeper, and that's the values here in meters, a deeper density, a shallower density layer. And it changes by about 50 meters. So that's, if you quantify that is quite an intense cyclone. Here's another example where it crosses inside and it comes to a shallower density surface. So again, it's all consistent. We have consistent observations from different platforms of cyclone. Okay. And we also see that there's inertial oscillations going on, which kind of obstruct things. You can see it here. You can see some weird pathways. It's not quite circular, is it? Right? And these cusps here, and here it's more clear with those that have left already. Inertial oscillations, it's what happens to a particle on Earth when it just has no external force other than Coriolis acting on it. So it just revolves twice daily, basically, in our area. That's an example from different, from some historical observations where you can see a lot of inertial oscillations, just so you see what they look like. So basically, okay, and I'll get to them in a second, but so what I want to say is that this vortex its size fits what we generally define as a mesoscale. It's about 10 kilometers. And I'll show you in a second that it's also an intense one. Its vorticity is high, so it's dynamically correct to say it's a mesoscale. But it's different from most sub-mesoscale, which I've shown you in the animations, in the model, and so on, because those are created because of the mixed layer instabilities that I've mentioned, whereas this one was formed from the boundary current. It's a boundary current type of instability. It was sort of created there locally and then captured, and therefore it has a different thickness. So the standard sub-mesoscales, they have the thickness of the mixed layer, so I'll say 50 meters, because that's what they were created from. Whereas the one we saw it just from the glider thickness of the density surfaces that it affected, it reaches 200 meters or so. So that's consistent with a boundary current generation source, because that's about the depth of the boundary current, a couple hundred meters. So it's a different type of source of sub-mesoscale. And perhaps that's why we can observe it in summer, because generally we need a deep mix layer that happens in winter to form the sub-mesoscale eddies, but it can form in different ways. We saw that there's small scales on the boundary current year-round, and you can ask me later about how it's formed, and we have some answers. But it happens, excuse me, but it does happen at the boundary current, that's the bottom line. And then if it's captured from there to the interior, all of a sudden you have sub-mesoscales in the interior in summertime. All right. That's about the vertical structure and the source. That's an example from observation of an eddy, a different one where they actually transected across a cyclone, and you can see how the density surfaces rise to the surface, whereas the surface height concaves to the bottom, the opposite thing. So you have basically a balance of forces beneath it. That's why it happens. You have the pressure is balanced beneath. All right, what about this crazy pass, which is doesn't look like a circular vortex at all, right? Looks like a square vortex. So as I said, it's because of inertial oscillations, which are superimposed. So I've applied a technique called complex demodulation, which allows you to kind of, if you know what is, if there's like one specific frequency which is superimposed, in this case inertial oscillations, you know their frequency is the Earth's rotation rate, then you can sort of pull them out of the time series, and that's the separation you see here. The full velocity in the time series of one of the drifters is in blue, and the eddy is in orange, and then in black is the inertial oscillation. So we have the separation, and then if I plot just the eddy part, instead of looking like that, it does look circular. So it looks like it works. So we understand why it looks this way. It's basically a lot of inertial oscillations, and they can be important in terms of mixing and turbulence inside the eddy, and I'll allude to this in a couple of minutes. But then we can take this idea further, the idea of sort of not just saying, oh, we just have an eddy here. As I said, we have many different scales happening at once, and we can use a more sophisticated technique, and it's sort of a generalization of this complex demodulation where you're seeing one frequency. In this case, you don't assume frequency, and you use the wavelet transform. So this is an example from a different case. I didn't put a paper name here. It's by Jonathan Lilly. So it's some sort of synthetic circulation path or paths of a particle which they've created. It looks like that. So it looks like an eddy which is moving around. And when you do the wavelet transform, you get, at every time, you get different intensities of the flow at different frequencies. So you get, at every time you get what are the sort of frequencies of change which are most important. And then based on this, there's a sophisticated technique, again from Jonathan Lilly, that it's called wavelet bridge analysis, which allows you to kind of identify eddies within it. Basically, based on eddy has a specific frequency of rotation, so you can identify it in the wavelet transform. At every time you can identify that specific frequency. And if we apply it to our data set, to different drifters, each drifter gets now an ellipse of rotation estimated from this technique. And it seems pretty consistent. From different drifters, you get they all sort of overlap, and the bigger ones are generally outside of the smaller ones. So it looks like it's working well, generally. Sometimes they sort of overlap in funny ways, and it might be because it's not working perfectly, or it might be because there's different instabilities in the eddy, so it's not a perfect eddy anymore. And the ones in the side experience a somewhat different eddy than the ones in the center. But in any case, the power of this technique is that from each drifter alone, you can get a vorticity value. And I forgot to say, from the complex demodulation on its own, then if you compare the residual, sort of the eddy time series, the eddy velocity, and you compare for two different particles, two different drifters, the difference, if you do it properly, gives you the vorticity. I told you the difference in velocities across a couple of layers which side up against each other. So the vorticity comes out as around 1 if you do this, which is, as I said, the Rossby number of 1, meaning inertia is important, Earth's rotation is not in full control anymore. So it is sub-mesoscale, it's not it is as dynamically a sub-mesoscale vortex. It's not the strongest sub-mesoscales. You can sometimes get even like 10 or so in these units with strong window sub-mesoscales, but it is something in summer. And then with this technique, we can get the full profile of vorticity versus distance from the center, eddy radius, and it looks like at the center it reached even higher, like 1.5 or more. But this is preliminary. So the black ones are for different drifters, different lines for different drifters, which were in different areas, and the red is just some sort of fit regression. Okay. And then finally, So I derived the properties of the vortex to kind of show you. I mean, we saw just quantitatively that it can carry material coherently, right? It carried the chlorophyll patch for 2.5 weeks, but I've shown you that it is sub-mesoscale dynamically in a couple of different ways. But I had to assume some things, you know, in the complex demodulation or in the wavelet technique. And there's another technique where you don't assume anything. You basically, if you have 3 drifters or more, from their relative motions, you can just directly calculate the convergence between them. So that this sort of component, the relative velocity towards each other, toward the center of mass, the vorticity, which is again how they slide against each other, and also strain, which is this sort of motion, which can converge in one axis and diverge on the other axis. So you can separate it exactly, but you just get it in the area between them, average on the area between them. And it's called differential kinematical properties, but in any case, it's basically pretty much directly calculating these properties from the drifter motions. If you apply that, this is time series for the first day or so, and vorticity is in the orange, and again you get values, average of all the drifters of about half to 1. Here there's a lack of data because of some, they were too close. Never mind, I can tell you why, but it's basically I flagged some data, there were some quality issues. And initially there's also strong convergence, that's in red. And in these same units which I've mentioned earlier, we get a convergence of -2 or so in the first hours. That's also very typical of sub-mesoscales and important in sort of bringing material towards its center. So initially we've put the drifters just outside of just at the periphery of the eddy. So the convergence makes sense initially. Now, the strain was present and strong the entire time as well. That's also typical. And then, okay. And then if you do the same thing for the entire 3 weeks that they were in the water, you can see how gradually the vorticity decreases. And you can see how basically the same things I've said about the strain being order 1 at the same time. So some sort of mechanism of instability was involved in the decrease of strength of the eddy. That's to be identified. And the last thing I want to show you is something about the turbulence inside the eddy. And I'm talking about vertical turbulence, vertical mixing. So if you have, you don't have vertical turbulent mixing, you basically have just molecular diffusion. It's a super slow process. You get very little done with that at sea. And once you have vorticity, once you have turbulence, you can mix things up faster. But when you have stratification, that reduces the strength of the vertical mixing. Horizontal mixing is much easier than vertical mixing because of stratification, which we have here. But it turns out that inside some mesoscale eddies, you can have heightened this small-scale turbulence and heightened mixing for that reason. And we had on board an instrument called a microstructure profiler. It's a very sophisticated instrument. And you basically, I didn't put a picture unfortunately, but you basically drop it from the side of the ship with a tether that is attached to it, but it's not stretched. So it's in free fall, it falls freely. And as it falls freely, it measures in high frequency, 100 hertz or so, 100 times per second. It measures very small scale variations in temperature and in velocity. From that, it can reduce turbulence and mixing. And I won't get into it, but I'll just show you a couple of results. So these are, we measured at 3 different points at, on the 22nd of June. And you can see the drifters were moving here, and they're at the edge of the eddy. So basically, we measured at these 3 points. So we're going from inside the eddy towards its edge and outside. That's the chlorophyll patch. So the first point was indeed had a deeper thermocline, shallower thermocline. You had colder temperature at the same depth as the later ones, and that's consistent. So indeed, it means that in this case, we're closer to the center than in that case. And what we got is as follows. So that's these are profiles of we lower the instrument multiple times, and this is from the first point. We repeated 5 or 4 times in the first point, And you see here the dissipation rate is a function of depth. The energy dissipation rate from turbulent motions, which is proportional to the mixing. It can be shown instead. I can show you the mixing instead of that, sort of proportional, but I'm showing the energy dissipation. And you also have two different curves here that are from two different sensors. So in the most violent event, they're very consistent, which is a good quality check. And basically, normal or typical values in quiescent areas of the ocean and sea are between 10 to the minus 9 and 10 to the minus 8. This is a log scale. Right? So we have a very violent event at 60 meters depth, which is under the Mixler, in the thermocline, and we have almost 10 to the minus 7. So it's a full order of magnitude or more of a sort of typical ocean mixing.
It's in meters, yeah? The units.
The depth is in meters, the energy dissipation is watts per kilogram. So there are areas where it's much higher, where you have straits and strong tide, very strong tides, stuff like that. But in places where you're far from, you don't have very narrow areas and you don't have strong tides and so on, these are quite high. And then in the next pass of the instrument, it measures sort of really the same thing. But there's variability. A couple of minutes later, it measured something different, slightly different. Still had some violent things. And that's typical of inertial oscillations or internal waves, which is sort of related to that, which we saw were active inside the eddy. That's the, now I'm showing the last point, the third point, which is sort of more at the periphery or maybe even outside the eddy. There's still some violent events with high dissipation, but it seems different. There's not as much going on at the same depth. In any case, it's preliminary and it's tough to say a lot about the dissipation from a few deployments, a few casts, but we did find heightened dissipation and mixing, which has implications for vertical material mixing as well. So I guess I won't read the summary. If there's questions, I'll be happy to answer that. Yeah, thank you.
If you translate the dissipation to turbulence diffusion coefficient, for example, what would be the scale of the turbulent diffusion coefficient in meters?
In meters square per second, it's I think it would be something like 10 to the minus. No, I don't know. I can't recall right now what are typical values for this specific. I mean, it's significant in that it would be an order of magnitude more than the background levels or typical levels. So yeah, if it's significant for a specific problem or not, depends. I don't know how to say.
It's a full lecture, and it's way too much to absorb in an hour. Thank you very much for presenting such. I have maybe comments more than questions. Number one, in this area of the Mediterranean, it's very hard to distinguish between the inertial oscillations and the tidal signal. Or about 30-something degrees, 32, 34, and
the frequencies are very close. The frequencies are very close in our area.
Are almost identical, I would say.
Yeah.
So it's not clear whether you really see the inertial oscillation. Number two, the focus here is mainly on the surface observations, both satellites and the drifters. It might be only the numerical model can supplement the information from what happens below the surface, and I think there's probably more in what you presented.
Well, I've shown just a little bit of the glider data. There's much more. And we also took deep measurements from the ship, but besides from the microstructure, but I haven't shown it.
And
but it's a challenge.
I wanted to say with regard to the calculation of vorticity from pairs or triplets of drifters, the method you presented is actually applicable to very small differentials. You can somehow tailor find a difference to observe to the differential. basically. You can calculate the differences, the differentials from the differences. A somewhat more sophisticated way will be to calculate the vorticity and all other properties directly from the solution of each drifter trajectory. But that's a very different operation.
Let's talk about it later.
Unorthodox, so.
Okay.
And it's late.
Yes. Yeah, we are a bit late, so you're all welcome to the almost weekend gathering, and we'll be able